How are the roads in Ann Arbor?
Oh, they're not. I mean, they're not horrible now. They weren't great this morning. We got almost 7. I think we got almost 7 inches here.
The roads in Jackson apparently are horrible still.
Yeah.
And I know my road hasn't been plowed yet, so it was ice capade. My walk to work today was ice capades. So
yeah, our parking lot hasn't been plowed either.
oh, great. So you're pretty much trapped.
Yeah.
Unless you have one of those big pickup trucks, I can.
Yeah, no, I do not.
Yeah, well, can't have everything.
Nope.
Okay. Yesterday was the Great Fest. Georgia. Something for the
disaster. Because it was so snowy. It took me half an hour to get back to campus. And I left the car or no, I left there at 6 because we closed at 5:30. No, you just have 62 bars. But you're not. No, but like you can see it. I can't tell if it's your face, but it looks tiny and like it's darker than like the rest of it, like the surrounding portion. Well, it all depends. Like they don't have anything. No. Yeah, you well, when I walked in the door, there was 60. Just like, I'm hoping it's faster. But did you? Yeah. Well, you should probably do Right, yesterday.
Sierra, for some reason, I don't have lab as a kid. Can you get it?
Yeah, I'll get it.
I looked and I couldn't check. I couldn't find it. So I'm afraid I might have lost it.
I can set up machines and I can tear them and I can disconnect people, but I can't help people yet. What person? No. So, yeah. to supplement. I was just. Their track NCAA, the NAIA. I think it's today.
Oh, it's 2 days.
Yeah.
So they left, okay.
They left this morning.
Okay. And, if I gave Jenny stuff to you, would you give
Words are really hard to say. I'm not sure why.
Right, so the quiz, Dane, make sure you see Mrs. Schaefer to take it. I'll send it to her. Make sure you do it before Wednesday, okay?
I remember. To be good on the old. Yeah. Or I could just write content, because how many other contents do you got? No. How many other practices?
All righty.
It's like 3 solid seconds. That's just
All right, given our inclement weather today, we're doing Zoom, so this is essentially for those who couldn't be here. So we are working our way essentially down the grade We talked about the cerebrum. So those are the derivatives of the telencephalon. We talked briefly about the thalamus, and now we are taking a look at the hypothalamus. So the thalamus, the epithalamus, which consists of the pineal body, which makes melatonin, which is associated with circadian rhythms. And now we're going to look at the hypothalamus. So the hypothalamus is a highly integrated part of the brain. It's part of the limbic system, but it's also a part of the brain that communicates with lots of other parts of the brain besides the limbic system. Some of the main functions that can be mapped effectively to the hypothalamus would include things like feeding, fighting, fleeing, feeling, and fornicating. I chose that word because it started with F, so it was a lot easier to remember if it's 5 Fs. So that's just a word for the sex drive. That's all that means. So feeding, fighting, fleeing, feeling, fornicating, those are the 5 Fs that you can map to the limbic system, but also to the hypothalamus. Also mapping effectively to the hypothalamus is temperature control. When you take a really nice close look at the hypothalamus, you'll notice that there are a lot of nuclei in the hypothalamus. Each of these nuclei essentially, at least when it comes to animals, but also when it comes to humans, based on information we have from lesions in these particular nuclei, it's known that some of these nuclei essentially are responsible for certain types of functions. So this particular nucleus here, for example, the preoptic nucleus, is known to play a really important role in thermoregulation. Interestingly, it also plays a role in sexual behavior. The preoptic nucleus is the nucleus that also releases gonadotropin releasing hormone. That will stimulate the anterior lobe of the pituitary to release gonadotropins. The two gonadotropins being follicle stimulating hormone and luteinizing hormone. So the release of this releasing hormone maps to that preoptic area, as does thermoregulation. There are two other nuclei that are important. The paraventricular nucleus up here, that is important because it releases a peptide hormone that is stored in the posterior pituitary called oxytocin. Oxytocin is quite important for childbirth. During that time, oxytocin is released at very high levels. However, lower, more routine levels of oxytocin are released while people are involved in friendships. And the cool feelings you get because you have certain friendships and also closer relationships, lifelong relationships, in fact, are bonded together by oxytocin. So a lot of work, not just from animal studies, but also from human studies, have shown that, in fact, friendship and even close relationships, marriage relationships, things like that, part of the pair bonding is a result of this routine release of oxytocin. If I can make a perhaps integrative comment about oxytocin since I get to teach here. I can actually talk about things like this. Something scripture says in Hebrews chapter 13, it says, let marriage be honored by all and the marriage bed kept pure. For God will judge the sexually immoral and the adulterer. That business about the marriage bed being kept pure. When I was in high school, people used to say to me, what's the big deal? It's just sex. I think the Bible had it right. No, it's not just sex. You're forming a bond with that person, whether you like it or not. We know today you are forming a bond with that person. It's not just sex. You're making oxytocin that draws you together. And this is the problem with the hookup culture. It tries to deny something that is biologically real about ourselves. It says we can essentially try to stick together and become unadhered, and then try it again and unadhere and try it again and unadhere. And you know what happens when you do that eventually? You become like tape that no longer sticks because your adhesive is all worn out. You become resistant to oxytocin. God made us to be drawn together, to be bonded to someone for life in marriage. And yet when you constantly switch one partner to another, essentially, you wear out the oxytocin response. So I think thousands of years ago, before anyone ever identified oxytocin, the Bible had it right. Shucks, who'd have known? Who'd have known? So that is the paraventricular nucleus. Now the paraventricular nucleus makes oxytocin, which is released by the posterior pituitary. There's another hormone that is also released by the posterior pituitary, and that is you see the orange all right? I don't know which ones you can. Diuretic hormone. Antidiuretic hormone, sometimes called vasopressin. That's another term for it. You may see that term occasionally. Now that maps to the supraoptic nucleus right here, just above the optic chiasm here, where the two optic nerves come and fuse. So right above that, that's your supraoptic nucleus. That is the source essentially of antidiuretic hormone. And so that has axons that go through the infundibulum, as it's called. The paraventricular nucleus has axons that go also through this. They will release their hormones into fenestrated capillaries that will then take them to where they need to go. Yes? Dan says the slides are not moving. Let's try. Okay, for this to work, then we need to do this. Okay, let's try this again. Oh, oops. I hate it when that happens. Okay. Take two. Participants can now see your screen. Oh boy, that just makes me warm and fuzzy. All right, now are they moving?
We're good now. Thank you.
They're good now. Okay, good. All right. Good. Okay, and we talked before about the lateral nucleus. Lateral nucleus isn't on here. There's a lateral nucleus and the ventral medial nucleus that play a role in appetite generation and appetite suppression. And down here we have this structure called the mammillary body. Mammillary body is important in so-called episodic memory. Episodic memory. So, Bracken, you remember that fight you got into in second grade where you whooped the class bully, showed him one? Right, that's an episode. Synthesis of that short-term memory into long-term memory was through the mammillary body. Episodic memory. Okay, so body temperatures, we said the preoptic area, and then the pituitary gland, which extends. The pituitary gland has two lobes, one that's more hormonally based, the anterior lobe, and the posterior lobe, which is more neural based. It's connected by a stalk called the infundibulum, through which you have axon tracts, just like that are shown here. These go to the supraoptic and the paraventricular nucleus. And if you need a way to remember that, a dumb mnemonic is SAD, supraoptic, makes antidiuretic hormone, and then pox. SAD pox. When you get the chicken pox, you're sad, SAD pox. Paraventricular makes oxytocin. Supraoptic makes antidiuretic hormone, SAD pox. That's my stupid mnemonic for remembering which makes which. The hypothalamus, as we said, makes releasing hormones. Those releasing hormones will regulate the release of the trophic hormones made by the anterior pituitary. I think that's everything I wanted to say about the hypothalamus. Any questions on the hypothalamus? All right, moving on to the midbrain. So between the diencephalon and the pons is that structure called the midbrain. And the midbrain has several nuclei in it that are of some importance. So you have 4 rounded elevations on the dorsal side of the midbrain, and collectively, those little bumps are called corpora quadrigemina, which means 4 bumps, basically. Well, 4 small bodies, but. And if you look essentially at a sagittal section of a brain, you can see these 4 bumps here. Notice the bump on the top is bigger than the bump on the bottom. But collectively, they're paired, so there's 4 of them. Those are the corpora quadrigemina, the corpora quadrigemina. The upper of those 2 bumps is the so-called superior colliculi. Superior colliculi. The superior colliculi are involved in visual reflexes. Visual reflexes. Visual reflexes could be, say something all of a sudden runs past you and your eyes go to that thing. This happened to me this morning. We have 2 cats, and the cat in the morning demands to be fed. And if you wait, the cat will be quite upset with you. So after my shower, I went, got dressed, went into the kitchen, and all of a sudden I see this something, all of a sudden just in the peripheral vision, like that, and all of a sudden, both eyes simply went that way. It was the cat. That was the cat telling me, you had better feed me or you will pay for it. So that's a visual sort of reflex. The other sort of thing is when you were kids, did you ever do lollipop, that sort of thing, you blink. Something was close to you like that, you blink. That's another example of a visual reflex. Those types of reflexes are mediated by neurons that go through, whose tracks go through the superior colliculus. The smaller ones, the inferior colliculi, those are centers for auditory information. We're going to do a reflex lab where you're going to take a metronome and you're going to put it essentially around the head while someone's eyes are shut, and they have to tell you where the sound is. We're going to discover that our hearing is good for detail, it's lousy for directionality. So people won't be able to determine with one ear plug if the phone is here or here sometimes. if it's here or out here. Directionality, we don't do directionality so well. And, but these auditory reflexes essentially are due to tracts that go through the inferior colliculus. The midbrain also contains the so-called cerebral peduncles. And if you were to take a brain and make a transverse section right through the midbrain, that's essentially what you'd see. So this stalk that supports the rest of the brain, that's called the cerebral peduncles. That black stuff that you see there, that is the substantia nigra. It really stares at you, doesn't it? That little hole there that looks like a toothpick could fit in it, that essentially is the cerebral aqueduct through which cerebrospinal fluid is flowing into the fourth ventricle down by the cerebellum. So notice as you look at this structure, there's lots and lots and lots and lots of white matter, aren't there? That's due to the fact that there are tons of ascending and descending tracts. Now, another structure in this area is the so-called red nucleus, the red nucleus. The red nucleus is extremely important for flexor muscles, particularly in the upper part of your body. Now, if you have severe damage to the brain above or below the red nucleus, that's going to determine your posture when you have that damage. There is a posture usually, if someone has damage above the red nucleus, because the red nucleus is no longer inhibited, the person will usually hold the arms like this, and the feet will be pointed like that. That's called decoricate. Decoricate. When we remember this, is the arms are close to the core of the body. Decoricate. Fibers come down, they inhibit the red nucleus. You disinhibit it, those flexors now get activated. Now, if you have damage below the red nucleus, now the arms will be out like this, and the feet will be out like that, and that is decerebrate. Decerebrate. You guys remember, any of you guys who watch football? He was the San Diego Chargers, Charles Parham, when he got injured in the end zone. You remember, it was Thursday Night Football? No? Help me out, guys.
He got knocked out.
He got knocked out, and the first thing, when he hit the ground, he did this. That's an example of a concussion. You essentially get activation of the brainstem, and you get, that's called framing. That's a framing response. And that is an example, essentially, because of the trauma to the brain, you are disinhibiting the red nucleus. So it gets activated, and so you get that framing response. That's an example of a concussion. There was a soccer player who had a blow to the head. He did the same thing. Belgian chap. I couldn't pronounce his name anyway, probably. French and I don't get on quite very well. That framing response, as you see that, in fact, trainers, that'll be something that you're taught to look for if someone has a head, blow to the head. First thing is ABC, airway, breathing, circulation, but then you look for that, because if you see that, it means you have to stabilize the head. You're supposed to put your hands under the head, make sure it's stable, and then you get the forward. But that response is due to disinhibition of the red nucleus. So the red nucleus, it's this area of gray matter in the midbrain. It has a lot of connections with the cerebellum. It's involved with posture, motor coordination, and things like that. And if you get damage, disinhibition of it can tell you something essentially about the level of the damage and so on and so forth. Buddha Baker, when he got hit too, Buddha Baker also, the one arm, did that. That's another example of a framing response when he got injured in was the playoffs, or was it? Yeah, it was the playoffs. That was another example. Didn't need to do that. There, okay. So the midbrain also has these sets of dopaminergic neurons, and the nigrostriatal projects from the substantia nigra to the corpus striatum, or to the basal, other parts of the basal ganglia, depending upon whether it's a direct or indirect pathway. These are necessary for voluntary motion, for initiation and coordination of voluntary motion. Learning, motor learning is also a part of this pathway as well, the nigrostriatal system. This is just meant to show you essentially some parts of the basal ganglia and their connection essentially with the substantia nigra. And here's the different parts of it and blah, blah, blah. We've talked bits already. I don't want to belabor the point there. And this simply just recapitulates what we talked about before, the indirect pathway, the direct pathway, and blah, blah. I don't want to go over that again. I've already gone over that. The other dopaminergic neuron that you have in the midbrain is this thing called the VTA, the ventral tegmental area, which also has dopaminergic neurons. They project to the forebrain, in particular to a part of the forebrain called the nucleus accumbens, which is right underneath, essentially, as the forebrain curves around. It's that area right beneath there. This is the mesolimbic system that's involved with reward and pleasure, involved with doing things like beating I woo twice, something like that, that rush you get. I struck her out, I kicked her butt, that rush you get, essentially, that's the mesolimbic system. And this is taken from the book. This is really a picture that shows you essentially these two pathways. So here's your nucleus accumbens here, and then also the prefrontal cortex, that's above the planning. So that helps you, this is part essentially of planning. Do I play video games or do I study physiology? And then the nigrostriatal system is in blue, and you can see it has many connections with the basal ganglia. The VTA, notice, is higher in the midbrain than the substantia nigra. Now, another set of neurons that you have in the midbrain is the locus ceruleus. The locus ceruleus is the source of most of your norepinephrine-based connections. Many, many fibers extend from the locus ceruleus into the prefrontal cortex. They're involved with alertness and also with focus and what have you, and decreased stimulation of the prefrontal cortex by noradrenergic neurons seems to be the basis of attention deficit hyperactivity disorder in most cases. That particular condition is probably not monolithic, I'm guessing. That's my best guess with that. Some people respond to medication, others don't. So if you look essentially just about any addiction, from gambling to opiates to alcohol, what have you, the mesolimbic system is the system that tends to get activated. And mitigating essentially this activation, you don't stop the activation. Well, in some cases you do. If you look at medications that are used, say, for alcohol use disorder, most of them dampen essentially the effects of the mesolimbic system. So there's a drug called naltrexone dulls the dopaminergic effects because most of those come from opiate receptors. And by activating endogenous opiates, you activate that pathway. Naltrexone dulls that. The other one is a compensate. And a compensate, same thing, it just kind of takes the joy out of drinking yourself into a stupor or something like that. Questions about the midbrain? Okay, as we continue to descend, if you will. And now get to the hindbrain. So the hindbrain consists of the metencephalon and the myelencephalon. The metencephalon consists of the pons and the cerebellum. The pons looks like a paunch essentially on the ventral side of the hindbrain. And then on the dorsal side is the cerebellum. Below the pons is the medulla oblongata. That is the myelencephalon. So the pons is here in red. It's pretty hard to mistake. The pons, it looks like a paunch essentially. Yes. Yeah, also several things. Several things. There's lots of nuclei in here that do a lot of things. Breathing, heart rate, visual stimuli, things like that.
So are there like chemoreceptors and baroreceptors in the pons?
There are chemoreceptors for the baroreceptor response goes to the medulla
Okay.
through the tractus solitarius, what have you, and yeah, that's all.
But the
there.
chemoreflexes are in the pons?
Yes,
Okay.
yes. If you get increased pressure on the brain, you get what's called a tonsillar herniation. The tonsils of the cerebellum will push through the foramen magnum and will press on that, and then just your breathing and your heart stops. And
So is that like, that's not like the
no, that's different. Usually, if you have brain injury, your pressure is up there. Remember, you've got that tentorium that's here.
right?
That shuts that off. But if you get pressure here, either a tumor or something like that, you can get, or it could be fluid too. You get a tonsillar, those tonsillar herniations, severe.
Okay.
They're very severe. They're almost always fatal. You can also get Duray hemorrhage. What that is? If you get a
Like
lot of,
germ matter? Like,
yeah, no, it's DORET.
oh.
If you get a lot of pressure and this gets pushed down, the basilar artery here gets sheared, and you get all these hemorrhages here. That's called the Duray hemorrhage, and that's fatal. That's when it's not just going to go. Basically, that's fatal. That is, you get a lot of force on top of the head, so it shoves this down. That'll cause a Duray hemorrhage, and there's not much that can be done essentially if that happens. Yeah, nice topic after lunch, right? Okay, I'll keep going. Just yeah, wasn't even Bracken's fault this time. I usually get the brain Bracken for my off-road incursions. No, that's okay. All right, so the pons has lots and lots and lots and lots of fibers, and fibers that are going to connect to the cerebellum. Deeper fibers that are part of the motor and sensory tracts that are going back and forth between the spinal cord and the brain. They're going to pass through the pons and the medulla to the midbrain, and then eventually to the thalamus, and eventually to the cerebral cortex or what have you. There are also nuclei for several of the cranial nerves that you find in the pons. And so 5, 6, 7, and 8. Those cranial nerves, they have their nuclei in the pons. And then you also have, and this is what you were asking about, Katya, the respiratory centers of Mystic, pneumotaxic centers. They are important for the autonomic sense of breathing. That's why you don't have to think about breathing, which is nice for when you go to sleep. Those control the autonomic breathing.
Yeah, like, doesn't it help with like hypocapnia and stuff like that?
Yeah.
Okay.
So if you have hypercapnia, you breathe faster.
And hypo is still.
Hypo, then you don't breathe as fast. Yeah, they're controlled. So they're also controlled by the chemoreceptors that regulate.
So like, what are people? So like, people who are like, never mind. That's a stupid question. I answered it.
Oh, okay. There are some people who don't have autonomic control of breathing. They have something called Ondine's curse.
Okay.
If you have Ondine's curse, you have to sleep with a respirator.
So like, what causes sleep apnea?
Sleep apnea in children that causes SIDS does map in some cases to this area. Some people have abnormalities in this area, yes. But SIDS is caused by lots of different things, it turns out. So animal studies of kids who just stopped breathing of animals, those areas mapped essentially to these centers in the brainstem.
Doesn't it also because they don't have like the reflexes to like turn themselves over? Like
That too, yeah.
suffocating?
Those reflexes are not developed yet, so. And then also certain types of respiratory problems. So SIDS is much higher in households where people smoke, for example, or where there's a lot of pollution. SIDS rates are just really high. And so it's probably an inability to clear. And instead of clearing, you just stop breathing properly. Sleep apnea in kids will run in families sometimes, and you put a kid on a monitor, and then if the monitor goes off, you just wake them up.
Yeah,
And
yeah.
They that must be awful. It's bad enough that the kid's not letting you sleep, nothing bloody monitors.
So is the primary role of the pons kind of like the thalamus, and that's just a really big relay center for a lot of stuff? Or does it have
Partially, yeah, but there are also nuclei that are the center of certain functions. So these two, for example, Dussen's is quite important for muscles of the eye and vestibular cochlear, of course, that's a sense of hearing. Facial as well, that's the muscles of facial expression. Those are all innervated by the facial muscle. Those nuclei are essentially the source of those particular cranial nerves. So it's that and more, shall we say. This shows you some of the locations of some of these particular structures. So we have these respiratory centers, as you can see, they're essentially distributed throughout the pons and then some are even in the medulla. On the dorsal side, there is a rather ill-defined group of neurons that form a column that goes up the dorsal side, and this is called the reticular formation. The reticular formation is known to play a role in wakefulness and alertness and what have you. The onset of sleep, for example, requires the suppression of the reticular center. If you have damage to the reticular center, you'll have trouble with wakefulness and alertness and arousal and what have you. The cerebellum, boy, I wish we had time to talk about the cerebellum. The cerebellum, the way it does business is remarkably interesting. So this, when you look at a brain and you turn the brain essentially to its back, it's probably the structure that kind of leaps at you in terms of its presence there. So this is a structure that has white matter on the inside, gray matter on the outside. It's very highly infolded. These enfoldings are called folia. The cerebellum is involved with motor coordination. When we talk about fine motor function, we're talking about the cerebellum. So a good example would be, hey, Bethany, you got your keys? Yeah. Oh, okay. Shut your eyes. Go through your pocket. Try to find your room key, just using your touch. Okay, did you get the right key? How'd you know it was your room key?
I knew it was longer than all the other ones.
Okay, you can tell that fine touch, if she didn't damage cerebellum, she didn't do that. That fine touch. Yeah. That fine touch, fine motor skills, those are things essentially that map to the cerebellum. The other thing that the cerebellum gets a lot of information from are proprioceptors, muscle spindle fibers, Golgi tendon organs, from joints and muscles, and they play a role in posture. So there's a test, and those of you who will be PTs, you will do this test, the Rummer test. This test? So you have the patient essentially put their feet together and cross their arms and close their eyes, and if they start, doing this sort of thing, that says that they've got usually some sort of issue with the cerebellum. So if they do this, they say relatively still, that says that their cerebellum is sound. As you get older, you may wobble just a little bit. I turned 61 in April, so hey, you got me some slack. But that Romberg test is one of the first tests normally you'll do if you're looking to see essentially someone's the integrity of their cerebellum. And then the other thing you do is you'd have them walk, and damage to the cerebellum may cause these things called hemibolismus. Oh gosh, am I gonna spell this right? In this case, instead of a smooth motion, you'll get something like this. That sort of thing, or if you have them, the other test you do is you just have them hold their arm out. Someone with hemibolismus would be like that. That's due to damage to the cerebellum. And that's simply because the proprioceptors here, which are detecting essentially position of a limb organ or something like that, they can't tell the cerebellum where they are. So it has to keep adjusting and readjusting and stuff like that.
So our hand trimmers related to that as well? It's like what
Yes.
makes them without-
Essential tremors. Essential tremors. There's damage to the cerebellum will cause something called intention tremors. Whereas with Parkinson's, you have the resting tremors. Intention tremors, when you try to do something, you start motion, you get this because you can't, there's that motion, you can't eliminate the unwanted motion. So the other thing that you can see, there's an exercise you can do. This repetitive sort of motion, you just have them go one up, one down, and just have them repeat it. Now, most people, in fact, just put your pen down and just do that. That's it, no big deal. People with a damaged cerebellum can't do that. That's called dysdiadechokinesia. Dysdiadechokinesia. And that is due to damage to the cerebellum. So repetitive action, fine motor skills, information coming from proprioceptors and things like that tell you about limb position and things like that. That's all cerebellum based. That's a skill. Little kids will have trouble with that, but they can learn how to do it. And that's motor learning. So think about when you start playing softball. You had to learn how to throw. You don't throw like this, you get the arm up. My daughter just mastered that. She's marrying a bloody baseball player. She just learned to throw like this and not like this. Emily, how do you know that? So that's a skill she had to learn, and that's essentially cerebellum based. Batting, essentially, being able to hand-eye see the ball, drive the ball, make sure essentially you're hitting the ball so that it doesn't end up in the first base glove, essentially. Trying to get, those are all skills essentially, and learn those are cerebellum based. New sorts of things. Say, for example, tomorrow you took up rock climbing. That'd be a new set of skills that you'd have to learn. That's all cerebellum based, essentially. So the cerebellum also helps you learn muscle memory. That thing we call muscle memory, very cerebellum based. And what have you. So this thing, it gets fibers from white and gray matter, red nucleus, motor areas, and what have you. They pass into the cerebellum. So the cerebellum, when you look at it, there is a so-called anterior lobe. The anterior lobe is separated from the posterior lobe by the so-called primary fissure. The cerebellum is turned like that. The nodular flocculonodular lobe is kind of inside. You have to cut the cerebellum off in order to see that. And it's this fluffy stuff, essentially, as the cerebellum wings around like that. So those are the three lobes. You also have three areas. You have lateral areas, and then you have a more medial area, and then you have areas, and damage to each of those will produce different types of events. So damage, for example, right into the center of the cerebellum will tend to cause truncal truncal problems and proximal limb issues, whereas damage to the lateral areas will tend to affect the more distal limbs and that functions of those areas. So if you take a look at the cerebellum, it has a variety of very interesting different cell types. One of the cell types you see is the so-called Purkinje neuron. And a Purkinje neuron typically has a axon that is extremely highly branched. So this axon on it is very big. And when you look at Purkinje fibers, Purkinje neurons, you can't mistake them. They're so big relative to everything else. And those Purkinje neurons are some of the most important of the cerebellum. And this just shows you essentially the way they're connected. I don't want to read you the riot act on this, but just to show you essentially the different parts of the cerebellum are associated with different parts of motion. So the flocculonodular lobe tends to be involved with coordinated balance and eye movements. And then the more medial part is about proper execution of coordinated motion. And then the more lateral parts are associated with planning, coordinated in time movement sequences and things like that. Now, proprioceptors are organs they're sensory organs in tendons and in joints, and they provide information about the position of limbs. There is a lab essentially you can run where you put someone in, you have these ugly sweaters that you have for everyone. You put someone in an ugly sweater, and then with them blindfolded, you lift the limb, and because of the thick sweater, they can't feel you touching them. But no matter where you put the limb, they know where the limb is. If you say, "Tell me," point with the other hand where the limb is. They'll tell you, they get it right every time. That's proprioception. You just feel where it is, and that's proprioception. And proprioceptors give a lot of input to the cerebellum, and they give you this sense of body consciousness. And damage to the cerebellum produces conditions called ataxia. We have a lack of coordination, and that lack of coordination means that you have trouble estimating the distance to something. You will overreach or what have you. You have errors in direction, you have errors in speed and force. Those are examples of ataxia, and they map to the cerebellum. A good test for this is the finger to the nose test. So you have someone close their eyes and then that. Someone with damage to the cerebellum can't do that because again, they can't sense their limb. And again, also the speed, they'll slap themselves in the face sometimes. There's a video of an Irish neurologist. What's his name? I can't remember his name, but I think I've got some of his videos on the website. Giving tests to people, you can see some of the results of damage to the cerebellum, where he tries to have them do this test, they can't do it because of the damage. And he's a good Irish chap with a wonderful Irish lilt, and he's a very gentle bedside manner. They're worth watching if you want to see what a good clinician who really cares about his patients and is very gentle looks like. What's his name? I can't remember his name. His videos are really good though. He's from the University of Dublin. So ataxia, particularly damage to the lateral cerebellum, is characterized by intention tremors. Those differ from the resting tremors of Parkinson's. And then we get to the medulla. And the medulla essentially is the last stop before we get to the spinal cord. So the medulla is the only derivative of the myelencephalon. You've got lots and lots and lots of fiber tracts. Many of those will cross over to the other side. They decussate within the medulla. One of the fiber tracts that crosses over in the medulla are the so-called pyramidal tracts. pyramidal tracts. They're called pyramidal tracts because if you stain a sagittal section of the medulla, the tracts, because they're crossing over, they make a little pyramid. That's why they're called pyramidal tracts. Pyramidal tracts are motor tracts. That's why those neurons are typically called pyramidal neurons. Hence, the right side of the brain motor-wise will control the left side of the body and so on and so forth. There are lots of cranial nerve nuclei found in the medulla. So cranial nerves 8 and 9 and 10 and 11 and 12, their nuclei are found in the medulla. So number 10 is the vagus nerve. The vagus nerve comes from the Latin term from which we get our word vagrant. Vagrant means someone who's wandering. The vagus nerve wanders. It wanders all over your body. It goes to the GI tract, and it's the wandering nerve, hence the term vagus nerve. There are other nuclei that are sensory in nature, and they will send their fibers to the thalamus and then to the somatosensory cortex right behind the motor cortex, the post-central gyrus. Cardiac centers are also found in the medulla, and these are so-called vital centers. So so-called vasomotor centers controls the autonomic innervation of blood vessels that will determine whether blood vessels constrict or relax. And then the so-called vital center also includes the so-called cardiac control center. And that will determine if your heart rate goes up or down. That's associated with what Katya asked about the baroreceptor response. We'll talk more about that when we get to the heart. But those are also in the medulla. And a few of the respiratory centers are also in the medulla as well. The reticular formation, as you can see, goes down to the medulla. General anesthetics will tend to suppress the reticular formation. They tend to do that by potentiating the activity of the neurotransmitter gamma-aminobutyric acid, GABA. GABA is an inhibitory neurotransmitter. By activating GABA neurotransmission or GABAergic circuits, you suppress the reticular system, and that's why you very promptly fall asleep. So the reticular system is relatively nonspecific, but the reticular system nuclei have lots of fibers that will connect to lots of places in the cerebral cortex to essentially increase awareness, increase arousal, things like that. So this is just a survey of some of the nuclei, essentially. Here's our old buddy, the locus ceruleus. Here are the Raphe nuclei that are serotonergic. They connect with several other nuclei, some of which use dopamine, some of which use histamine, some of which use acetylcholine, and then this particular one, the lateral hypothalamus, uses a peptide called orexin. So this particular network, as you can see, is important in keeping us awake. Now, first generation antihistamines will inhibit this particular tubomammillary nucleus. By inhibiting that, that's why drugs like diphenhydramine, trade name Benadryl, and other types of first generation antihistamines will shut this down, and then shut the rest of it down and start sawing wood. So first generation antihistamines and other drugs with histaminergic inhibition activities will tend to be sedated. I still remember very vividly, I was in a virology class with a professor named Randy Pritchett. Randy Pritchett had a reputation for being remarkably boring. And this day was like no other. It was April, and at UC Davis, Davis is the olive capital of California. Guess what I am violently allergic to? Olive pollen. I would go into these paroxysmal rounds of sneezing. So I took a drug called chlorotrimazole, which is chlorpheniramine. Chlorpheniramine is a first generation antihistamine. Stopped my sneezing, but it blocked that. I remember my notes would go like this, and then my pen would just go like that. I'd fall asleep. And I'd wake up, and then my pen would just go like that. I fought so hard to stay awake. Pritchard was no help whatsoever. He was so boring. And he was a very good virologist, but holy Hannah, that guy was boring. And that's an example essentially of how drugs that block histamine receptors can cause you to go to sleep. I don't recommend taking Benadryl to fall asleep because Benadryl has anticholinergic activities as well. Acetylcholine is necessary for REM sleep. That's why it'll help you fall asleep, but the quality of your sleep will be poor. There are better ways to fall asleep. Now, don't take Benadryl. Also, after taking it several nights in a row, you get resistant to it. So these particular fibers, as we said, they are ones that connect throughout the cerebral cortex to maintain a state of consciousness. And so inhibiting particular nuclei that are rather central can now start to shut this down. And that is precisely how certain types of agents work, like certain anesthetics and what have you. And it turns out that this ventrolateral preoptic nucleus in the hypothalamus, if you inhibit that, that tends to be the switch that will shut everything else down. This one will release GABA. It releases galanin. It inhibits the tubomammillary nucleus. And that's inhibited during wakefulness. If you can get that thing going again, it will shut the whole thing down. In fact, that's how some anesthetics work. They disinhibit this nucleus and it shuts the whole thing down and you fall fast asleep. Very good. Any questions about the brain? Anything like that? No? Yes, Nona?
Is the Purkinje neurons the medulla the same set of fibers?
The density of neurons is the same as Purkinje fibers are in the cerebellum. They're in the cerebellum. And the density of neurons in the gray matter of the cerebellum is pretty high. Fibers, you have these things when you cut the cerebellum, you'll notice that there are several fiber tracts. They're called peduncles, cerebellar peduncles. There's a superior, medial, and inferior peduncle, and different tracts enter and exit through those different peduncles. And there's lots of tracts that come from lots of different places. All the information, neural information that comes from the cerebellum is inhibitory. The cerebellum does not activate anything. It's all inhibitory. So it's about refining motion. That's an important thing to, but without that inhibition, you get attention tremors and ataxia and what have you. That inhibition is important. All right. I don't mind finishing a little early for a Friday. So we'll pick this up on Monday. We'll talk about the spinal cord. And after that, and we have an exam on the 25th, 5th or 3rd? 5th, 25th, yeah, 25th, which is next Friday. Study hard, make me proud.
Yeah, so.
Dr. B, where does our exam information extend to?
The neurons. So the chapter, the lecture about neuron activity.
Okay,
After that, that's the only part that's on the exam.
okay, sounds good. Thank you.
All right.
I'll get that quiz taken
Okay.
Monday.
Okay.
All right, I'll see you then. Bye.